Okay, so ladies and gentlemen, let's continue with chapter 4 in the textbook of White. It is about differential equations in fluid flow, and the chapter in principle is about the derivation of the continuity equation, the momentum equation, the energy equation, and its applications, how we can use it. Now, if you look at the fluid mechanics course that you've done, it is a little bit isolated in terms of the rest of the work, where you've actually used an integral approach. So let's just stand back a little bit and look at what are the differences and what are the strengths of each method and when each method should be used. Okay. So in general, if we want to analyze fluid flow types of problems, then there are two approaches that we can use. The first one is typically what you've done in chapter 3 in the textbook of White, where you've derived all the equations, and then, as far as I know, you didn't apply it only in that chapter, but also quite widely in the textbook. Okay. So specifically in chapter 3, what you did is you have derived the integral relations for control volumes. Okay. So please divide your page in two. On the left-hand side, I'm going to do the integral ones, and on the right-hand side, the differential ones. Okay. So the integral relations of a control volume. Let's look at a typical problem. Let's suppose you are interested in a rocket. Okay. And the rocket typically will have a nozzle, and that would be its outlet velocity. And you are interested to know the forces on the rocket and all the acceleration. So the approach that you've used in the integral relationship is to look at the control volume around normally it can be a relatively large body, or it can be smaller. Okay. So there's the control volume, and then you've looked at everything happening over the control volume. So you've considered everything inside almost as a black box. Okay. Now, the result of this approach is that you could then derive the integral equation over a control volume for d rho dt multiplied by d. Take note that's volume. Okay, volume. Plus the sum of everything going in, rho multiplied by the area multiplied by the velocity, everything going in, minus everything going out, rho multiplied by the area multiplied by the velocity. Everything is ice, and that would be equal to 0. And that is the continuity equation, but it's the continuity equation in the format for integral types of relationships. Okay. And with this equation, we could then typically maybe solve the velocities over the boundary layer or the boundary volume. Similar equations are available for momentum, annular momentum, and energy. Okay, so similar types of equations are available for the momentum equation, annular momentum, and energy equations. And they are all known as integral relations. Now, what we're going to do now is we are going to look at chapter 4, in which we're going to look at the differential equations over or through a control volume, the differential ones. Now, if you would be interested in, for this rocket, again to study it, then what would be the differences in approach, or what can you get differently than with the integral approach? Okay. What is different now is that in the integral approach, what you can solve is what happens over the boundary, over the control volume, not the detail inside. So if you're interested in the nozzle, there's the nozzle, typically maybe like that, and you want to know the velocity at different places in the nozzle, then you cannot solve it with the integral approach. You have to do the differential approach. And the differential approach would typically end up where you have smaller control volumes, okay? And in each one of the control volumes, you want to solve the velocities or the temperatures or whatever. Okay, so that is the difference. So here you would like to solve small detail, and here you would like to solve everything moving over the control volume or out of the control volume. Okay, now the differential equations in comparison with the integral equations typically looks like this. Partial d rho dt plus ddx of rho u plus partial ddy of rho v plus partial ddz rho w is equal to 0. Okay. So the equations looks differently. You can do different things with them, but in principle they represent the same things. Continuity equation. Okay. Now what we're going to do today is we're going to derive this continuity equation. Okay. There's also, as I've said, a momentum equation. In the textbook there's an annular momentum equation and there's an energy equation. Okay. And as I've written it now, it is for a Cartesian coordinate system, x, y, and z. So each one of these equations can be developed for other coordinate systems, cylindrical, spherical, etc. And in the textbook, the authors had big fun showing all these equations. Okay. So, in different coordinate systems, and what we're going to do in this course is firstly, we're going to derive the continuity equation. Then the momentum equation, we're going to derive partly. Okay. And when we go through it, you will understand why. It is just in terms of the volume of writing, the volume of area that you need is very difficult. So if you ever need to do the momentum equation, and you have to derive it in detail, go and get yourself a big page, and do it on that. That is the best advice I can give you. Right. So let's start then with, all right. Before I forget, in terms of the differential equations, the main use are two things. As you've seen, you need these equations in your CFD course. Because that is the one that you're going to discretize and develop the equations from, and you're going to use procedures like the simple procedure to solve the equations. Okay. Now, before CFD, these equations were there, but the problem was that they were very, very complicated. Okay. Still cannot be solved, and there's still a Fields Medal for somebody that wants to solve it. Okay. To get the analytical solution of it. Okay. So, as typically as we are as engineers, we try to make things very simple first, and then from that, make it more complicated. So, a lot of work has been done where, firstly, assumptions was made in terms of practical problems. For example, let's consider steady state problems. Okay, so we throw out that term. We would say, let's suppose the density is constant, it is one-dimensional, etc. And then these equations were then used in geometries like, for example, between two flat plates to derive the velocity distributions, okay, or through a pipe, okay. And those solutions are critical when you develop something like a CFD code, because once you've done it, you're going to say, well, let me go and test it. Okay, and you're going to go back to these simple cases, and you're going to test and make sure that your CFD code gives what it should give. So they are very, very important. So what we're also going to do is, except for the fact that we're going to derive that partially, we are going to quickly look at some of these solutions and typically how they can be solved. Right. So let's start with, in your textbook specifically, paragraph 4.2, which is the differential equations for mass conservation. Okay, differential equations for mass conservation. And we do that by considering a control volume. And the control volume, in terms of its coordinate system, looks like this: x in that direction, y in that direction, and in that direction z. It has dx, in that direction, dy, and dz. So what we're going to do now is we're going to look at the mass flow rates in and out of the control volume. Okay. Now mass flow rate, as we know it, the mass flow rate is equal to rho multiplied by the volume flow rate. Just be careful for this Q here, that you do not think it's heat transfer. Okay, so this Q here is volume flow rate, or if you want to use another symbol, I think in some textbooks, or maybe even either one of Sengel, they use a funny type of V with something like that. So that is volume flow rate. Okay, so Q, let's write it like this. So Q is equal to, that symbol is, and the units would be cubic meters per second. The units, okay. Okay, so in terms of this definition that we know of the mass flow rate, we can also write that the mass flow rate is equal to rho multiplied by the velocity multiplied by area. That is just in general how we normally think of mass flow rate. You agree? So the mass flow rate would always be equal to the density multiplied by the volume, and this area would be the cross-sectional area. Okay. So if that is typically the tube, and the flow goes through there with a velocity, it would be the average velocity, and that would be the cross-sectional area of the tube, typically. Okay, now let's look at what is flowing into the control volume from the x direction. Okay. And the coordinate system, or the nomenclature that we use, is that the velocity vector v, okay, will consist out of the components u, v, and w, the velocities. Okay. U in the x direction, v in the y direction, and w in the z direction. Okay. So in terms of the mass flow rate going through that surface there, that would be equal to the density, okay, multiplied by the velocity, and it's the velocity in the x direction. So the x direction is u, okay, multiplied by the cross-sectional area. The cross-sectional area through which the flow occurs. And the cross-sectional area is this face here. You agree? So that is equal to dy multiplied by dz. Are you still happy? Right. Now we're going to use this approach of looking at small changes that you've done lots of times in mathematics, but sometimes you just have to go back and rethink what you are actually doing and what it actually means. So what I'm going to do is I'm just going to stop with this and I'm going to look at, in general, let's suppose you have a function of x, okay? And between dx, okay, obviously this can be coordinate system x, y, and that can be the origin. It doesn't matter. Okay. But in general, if that is equal to y, then we will say, well, that is equal to y plus dy dx multiplied by dx. Okay. Okay, in general. And the idea is that the smaller dx is, the better that would be a representation of a straight line. You agree? Okay. So what it actually means is, if I can just draw this maybe a little bit wider, okay, like that. And let's look at a very, very simple case of an equation that would represent something, the velocity or whatever. And the equation is y is equal to 2x plus 3. And let's suppose this value here would be equal to 3. Okay, what would the value be there? You would say, well, that's trivial. I mean, at least I know how to use y is equal to 2x plus c, especially if I give you x is equal to 4. Okay. So it would obviously be y is equal to 2 times 4 plus 3, and that would be equal to 11. You agree? So it's very, very simple. So what this actually means is that if we have a value here, then we would say the change in the value, or that value would be equal to that value plus the change, the gradient multiplied by delta x. You agree? Okay. So if we would use that, obviously I had the equation now. Okay, so if we would now use that approach, that one there, we would say the answer would be 3 plus the gradient, which would be 2, multiplied by dx, which is 4, and that is also equal to 11. So that is the foundations for what we are doing here. So any change would be this value plus the gradient multiplied by the distance. The principle of it. You understand? Okay. So if we now go to that face there, that face there, then the mass flow rate would be equal to rho u. I'm going to write it a little bit different now. Let me. No, I don't have. Okay, let me put it here. There's that arrow, and which I do not have enough space. Okay. So it would be equal to the y value, which would be equal to rho u dy dz. Okay, plus the gradient, which would be equal to d rho u multiplied by dx. and multiplied by dx. Okay. Or, if I just do a little bit of manipulation, I can write it as rho multiplied by u plus partial d rho u dx multiplied by dx multiplied by dy dz. I forgot my dy dz here. Okay. And my dx, there you go. Okay. Okay, so we've done it now in 1 dimensions. Now we also need to do it in the y direction and in the z direction. Now if you have a large piece of paper, then it would be good to write it out. I'm going to do it a little bit different now. I'm going to do it like this. I'm going to say, well, let's look at the direction. And then let's look at what happens at the inlet and what happens at the outlet. The directions would be x, y, and z. The z direction in terms of in the inlet will be rho multiplied by u multiplied by dy dz. And the outlet one would be equal to rho u plus d of rho u dx multiplied by dx multiplied by dy dz. Okay, then in the y direction it would be equal to rho multiplied by v. Okay, in the y direction, the velocity in the y direction, okay, not u but v. And now the surface area would be equal to surface area in the y direction would be that surface there, dx multiplied by dz. Okay? And then we do the same on the outlet side. Okay. And on the outlet side, we can write it as rho multiplied by v plus partial dv dy multiplied by dy and now multiplied by dx dz. Am I going too fast? Are you still with me? Okay. Now in the z direction, it would be equal to rho multiplied by w now. Okay, the velocity w. And the velocity w would go into the face of dx multiplied by dy, that one there. Dx dy, and in terms of the outlet, the same type of format, rho w plus partial rho w dz, dz multiplied by dx dy. Right, are you all happy? So now we know everything that's going in and out. Okay. So if I would now look at the continuity equation and I would say everything going in must be equal to everything going out, will you be happy? I see lots of heads. I hope there's somebody that would not be happy. What did we forget? Okay, the previous chapter, and obviously we do not do it a lot as engineers. We like things to be steady. We do not like changes as a function of time. The previous chapter was on how things changes as a function of time. So changes as a function of time, we also need to take into consideration here. Now, where does that now come from, and how are we going to do that? Well, let's use the simple example of a control volume. That same control volume. Okay. But let's make it schematically just a little bit bigger so that we can visualize it a little bit more. Okay. And what we do with this control volume is, it has a hole in, and we put in 3 kilograms per second of water at t equals 0. Okay, at t equals 0. Okay. And it's empty. Okay, t equals 0, it is empty. And the outlet is maybe smaller, or there might be many different reasons. The outlet mass flow rate is only 1 kilograms per second. So what is going to happen? Okay. So if we now take the same tank or the same control volume, and we would look at 10 minutes later or whatever, then in terms of this 3 kilograms per second still coming in, and that 1 kilograms per second going out, mass will be stored into the volume. Okay, you agree? And it will be stored at what rate? Every second, the mass of the control volume will become more by 2 kilograms. Every second, the weight, the mass will increase by 2 kilograms. Okay. So the mass increases at 2 kilograms per second. Okay. Right, let's go back to the chapter on the integral relations where we've looked at the continuity equation. Okay. The continuity equation in the chapter 3 for a control volume, doesn't matter what's in the inside. Do you see that term? Okay. That is the unsteady term that takes into consideration how the mass of the control volume changes. And this is exactly what we have here. Okay. So we can say that, so from the continuity equation, specifically the integral one, okay, then the surface integral over the control volume of partial d rho dt multiplied by dv plus, okay, the sum of I equal 1 to rho I, rho multiplied by the area multiplied by the velocity, everything going out, minus everything coming in, must be equal to 0. Okay. And that term there is exactly what is describing what is happening there. So what we can do is we can say, well, that would be equal to, because the control volume is so small, we can say dv is equal to dx, dy, dz, okay? So we can say that that term would be equal to partial d rho dt multiplied by dx, dy, dz when we do the integration over this very simple control volume. Right, so if we now think of the continuity equation, okay, if we say everything going in is equal to everything going out, normally that is true, okay, in steady state conditions. However, if it is not steady state, it should be everything going in is equal to everything going out plus the change in the mass of the control volume. Agree? So that is the real continuity equation. Right, so if we now look at everything going in of the control volume, which is then equal to everything going out of the control volume, plus partial d rho dt multiplied by dx, dy, dz, then that is the continuity equation. Okay. And this would be equal to all three that terms there. Okay. So everything going in would be the sum of those three terms. You agree? Okay. So we do have some writing to do, and let's do that. Rho u multiplied by dy dz plus rho v multiplied by dx dz plus rho v multiplied by dx dy, all three terms going in, okay, is equal to everything going out. Okay, so let's take the first one, rho multiplied by u plus partial d rho dx multiplied by dx multiplied by dy dz. Okay? I've written down now the first term, that one there. Okay. Now I also need to get in the other two. So let me try my best. Okay. So it is equal to rho multiplied by v plus partial density multiplied by the velocity multiplied by dy, dy multiplied by dx multiplied by dz, plus the last term, which is equal to rho multiplied by w plus d partial rho w dz, everything multiplied by dz multiplied by dx and dy, plus, okay, everything in, these three terms here, everything out, these three terms here, plus partial d rho dt multiplied by dx, dy, dz. Okay, I hope I didn't make a small u or a v or whatever error. If there is one, just correct it, but the principle now is important. Okay, you're all with me? Make sense? Right, okay, so now let's look at what happens now if we start evaluating all the terms. Rho u multiplied by dy dz. Rho u multiplied by dy dz. Okay? So, that term is equal to that term there. Rho u multiplied by dy dz, rho u multiplied by dy dz. All happy with that? Can do the same with this term. It's equal to that one, and that term is equal to that one there. Okay. Okay. What is left behind? These three terms here. Okay. Each one of them have a dx, a dy, and a dz. A dx, a dy, and a dz, just not in the same order. And again, dx, dy, and a dz, and a dx, dy, and a dz. So, we can take it out, and the result is partial d rho dt plus partial rho u multiplied by x plus partial rho v multiplied by dy plus partial rho w dz is equal to 0. I'm just going to clean the board on the side while you finish the writing there. Okay, so, and this is called the continuity equation. Okay, the continuity equation in a differential format. The continuity equation is in a differential format, and there are different ways in which you can go and write it in a more compact form. You've done it in mathematics. And one would be typically to write it as the rho dt plus the grot of rho v is equal to 0. Okay. So that is the other format in which this equation can be written in. Right, this equation has some special cases. Okay, special cases for this equation. Let's look at them. And there are two of them. Okay. I'm just going to write down the equation again. Partial d rho dt plus partial rho u dx plus partial rho v dy plus partial rho w dz is equal to 0. Right. The first case is for steady flow. Okay. That is the one that we as engineers normally would like to work with. It makes our lives more simple. And most design cases are for steady state conditions. Okay. However, things in life are not always steady state, of course. If you have a jet engine or an Airbus engine and you start it, then obviously you do not have steady state conditions. Okay. And if the pilot makes some certain changes, then again, you do not have steady state conditions, but then after that, they would prefer to fly in steady state conditions, and that would be our design conditions. Okay. So this is a very important case for us, and that is steady flow. What does steady mean? It means that rho does not change as function of time. Okay. So if I would go and get into that jet engine with my P2 tube, and I would sit there in the Airbus engine at any specific point, taking the measurements of the density as a function of time, then it should be a constant value. Okay, like that. Okay. The moment the Airbus will have a bird strike, then obviously, you know, things would change quite a lot. And if you didn't write off the engine, obviously, you know, things would go back to steady state conditions. Okay? So, for steady state conditions, it would mean that that first term would disappear. Okay? So, partial d rho dt would be equal to 0, and the result would be the equation of partial rho u dx plus partial rho v dy plus partial rho w dz is equal to 0. Okay, you happy with that? Right, and the next special case is for incompressible flow. Incompressible flow. Incompressible flow is when the density stays constant. Okay, so rho is a constant. Okay. Now suddenly, if I say that and that, what is now the difference between the two? Okay. What is now the difference between the two? I mean, density constant and density constant there also. So obviously, that one is a function of time. Density is constant, we would normally refer to the whole flow field. Okay. So let's suppose, and this would definitely not be a good example, but let's suppose that is the engine, okay, and of an Airbus, okay, and let's suppose that is X, okay. Then through the engine, the density is going to do something like that, okay. If we go and measure it at different points. Okay, so the density wouldn't be constant in an Airbus engine. Okay, but if the Airbus is flying at a Mach number smaller than 0.3, and we are interested in the airflow around it, then we can make the assumption that the density is constant. Okay, so air is a wonderful fluid for us as engineers. The Mach number is an indication of compressibility, okay, in fluid mechanics, compressibility. And from experiments we know that if the Mach number is smaller than 0.3, then the density changes is negligible. Okay. So, but that would now not be through the engine, it would be on the outside. Okay, so okay, so that would be maybe here on the wing, Mach number smaller than 0.3, and if we would then go and measure the density over the wing, it would be a constant. Okay, it would be a constant. Not a good example would be, let's put not air, but water through the engine. Okay, if you would put water through the engine, which I suppose can happen when the aeroplane decides it wants to go into the sea, okay, then the density is not going to change, the density is going to be a constant, and if it is a constant, okay, then if we look at this equation, it reduces to partial du dx plus partial dv dy plus partial dw dz is equal to 0. So that is the continuity equation for incompressible flow. Very important equation, and that we use quite a lot. Okay. So, ladies and gentlemen, the derivation of the continuity equation. Any questions? If not, thank you very much, and I'll see you again tomorrow.